Okay, so welcome to this next video in the playlist on group theory. In this video, what we're going to introduce is the concept of a centralizer and the concept of a normalizer. Okay, so the title for this video then is Centralizers and Normalizers. Okay, now in this video we're only going to introduce these concepts. We're not going to see why these concepts are so important. Okay, so we're just going to see the definitions of a centralizer and a normalizer, and we'll have a look at what the definition actually means, so what these things really are. Okay, but we're not going to see the great applications of these. These are things that we will use in upcoming videos in the playlist on group theory and beyond. Okay, so this video is just to introduce the concept of a centralizer and the concept of a normalizer. Okay, so we'll start off then with a centralizer. Okay, so firstly let's just do the setup. So what do we need to have in order to discuss a centralizer? Okay, so firstly we of course need a group. We are of course discussing group theory, so we need some arbitrary group. Okay, and I'll just remind you that a group consists of a set of symbols, which I'll draw here. Okay, along with a composition law defined on it, so here's the composition table, which allows you to compose any two elements from this set of symbols together to get a third element in this set of symbols. Okay, and that group composition table must obey the four axioms of group theory: closure, associativity, having an identity element, and having inverse elements. Okay, so we've got some arbitrary group, capital G here. And now the thing that we need in order to discuss centralizers and normalizers is some subset of the group capital G, some subset of the set that underlies the group capital G. Okay, so drawing a picture here, let's say we now represent the set that underlies the group as a box here. So let's represent our group here, and once again I'll colour it in red. And what I now need is some subset, some arbitrary subset, and I want to stress this doesn't need to be a special subset, it doesn't need to be a subgroup of capital G, it just needs to be an arbitrary subset of capital G. So whatever subset you like, okay, and I'll colour this subset in green here. Okay, so those are the two things that we need in order to begin a discussion of centralizers and normalizers. So we need a group, and we need a subset of the set that underlies that group. Okay, right, so what we're now going to do is we're going to define what is meant by the centralizer of the subset capital A in the group capital G. Okay, written like so. So capital C for centralizer, and I'll write down how you would speak this. So capital C is for centralizer, and then you'd call this the centralizer of the subset capital A here, and then this subscript here is the in G portion. So this is the centralizer of the subset capital A in the group capital G, and I'll colour code this in yellow. Okay, so what is actually meant then by the centralizer of a subset capital A in a group capital G? What does this mean? What's the definition of this? Okay, so the definition of this is that this is going to be a subset as well of the group. Okay, so it's going to be lots of elements of the group. It's going to be little g is an element of the group, but of course it's not just the entire group. These elements need to obey some property, so such that, okay, where little g, a g inverse is going to equal little a for all little a is an element of the set capital A. Now let me just explain exactly what that means. So basically this is saying that if I take any element from my subset capital A, so whatever little a I take from this subset capital A, and I might just add this onto the picture, so take some arbitrary little a from our subset capital A and conjugate it by this element little g. So take GA, G inverse. Okay, so conjugate little a by the element little g, then it must give me the element little a back again, and that's for all little a in the set capital A. So go through every single element of this set capital A, conjugate every single element by the element little g, and little g, when it conjugates the element little a, must send little a onto itself basically. So all of the elements of this subset capital A must be fixed by conjugation by any element of the centralizer of A and G. Okay, so going back to the picture then here to interpret what this actually means, what you're going to do is you're going to go through every element of the group, so I'll mark this on. You'll go through every little g is an element of our group capital G, okay, and for each one what you'll do is you'll ask, is it the case that this conjugates every element of the set capital A to give back the same element of capital A? So you'll go through all of the elements of this set capital A, and I'll mark some more of them on here. So you'll go through every single element of the set capital A, you'll conjugate every single element of the set capital A by this element little g, and you'll ask, are we getting the same answer back again? When I conjugate each and every element of this set capital A, is the answer the same element of the set capital A? And if it is true for absolutely all the elements of the set capital A, that when we conjugate them by little g, we get the same element back again, then we put that little g into the centralizer of A and G. So it's all elements of the group which fix all of the elements of the set capital A if you conjugate the elements of the set capital A by that element of the group. Okay, that is the definition then of the centralizer of a subset A in a group capital G. Okay, so this then is a subset of the elements of the group capital G. So what we can see blatantly is that this is a subset of the set that underlies the group capital G. So we can see blatantly that it is indeed a subset. However, you can probably guess what my next line is going to be. I claim that the centralizer of A and G is a very special subset of capital G, and this is true no matter what capital A is. So capital A doesn't need to be a special subset. The centralizer of A in G will always be a subgroup of capital G, no matter what subset capital A you use to create this centralizer. Okay, so this is the next thing that I want to show, that the centralizer of A in G is always going to be a subgroup of the group capital G. Okay, so we already know that it is indeed a subset of the group capital G. What we now need to show is that with the inherited composition law from the larger group capital G on it, the centralizer of A and G actually obeys the axioms of group theory. Okay, so again, there are 4 axioms of group theory. We've done this before in previous videos in this playlist. There are 4 axioms of group theory, and we know that when we're checking that a subset is a subgroup, we don't need to worry about the second axiom of group theory, associativity, because we know that if it wasn't the case that the inherited composition law on a subset obeyed associativity, then the composition law on the larger group wouldn't possibly be able to obey associativity, and therefore it wouldn't be a group. So as long as this is a group, then the inherited composition law on this subset of the group must obey associativity, so we don't need to worry about the second axiom of group theory. But we do need to check 1, 3 and 4. Okay, so let's do that now. So firstly, axiom number 1 of group theory, we need to check that the centralizer of A and G obeys closure. Okay, and what does that mean? That means that if we take little g1 and little g2 from this subset, so from the centralizer of A and G, CGA here, okay, so we take 2 arbitrary elements of the centralizer of A and G, we need to prove that if we if we compose the 2 of them together, we'll end up with another element in the centralizer of A and G. So what we want to show, okay, that G1 composed with G2, and I'll just write them next to each other to denote composed, is also an element of the centralizer of A and G. Okay, so this is the next thing that we need to show, that G1 composed with G2 is also an element of the centralizer of A in G. Okay, right. So, how are we going to show that then? Well, we're just going to apply the definition basically. So if we want to show that G1, G2 is an element of the centralizer of A and G, what does that involve doing? That involves showing that if we conjugate any element of the subset capital A by G1, G2, that we end up with that same element back again. So we need to show that G1 composed with G2 conjugating the element little a, so let's put the element little a in the middle, and then we need g1, g2 inverse here, okay, so I'm just conjugating the element little a by g1, g2 here. We need to show that this is equal to little a for absolutely all little a in this subset capital A. Okay, so this is what we need to show. Okay, so showing this is absolutely equivalent to showing this. This is just the definition of what it means to be in the centralizer of A in G. Okay, so before we go any further, let's just go over a little theorem that's interesting in its own right, but amazingly, which I've never actually gone through, I don't think, in any video in this playlist on group theory up to now. Okay, and that relates to what is the inverse of G1 composed with G2. Okay, so let's just have a little side part here. So what is the inverse element of G1 composed with G2? Well, my claim is that this is actually equal to G2 inverse composed with G1 inverse in the opposite order to the order that you compose G1 and G2 in. Okay, and the proof is absolutely trivial. All I need to show is that this thing that I have here composes with G1, G2 in either order to give me the identity. So let's firstly do it in this order. So we'll have G1 composed with G2, so the element, and now what I'm going to do is I'm going to compose this, and I might just write out the composition symbol to make it utterly blatant. Okay, I'm going to compose this with G2 inverse composed with G1 inverse. Okay, so let me just highlight this up. So here is my G2 inverse G1 inverse, which I'm claiming is G1 G2's inverse. Okay, and now I'm composing it with G1 G2 here, and of course this is going to equal the identity. And why is it going to equal the identity? Well, what I can do is just say, okay, let's compose G2 and G2 inverse together. That will give me the identity element. Okay, so this will become G1 composed with G1 inverse, because of course I can just get rid of the identity element from here, because the identity composes with anything to give that other thing back again. Okay, and then of course G1, G1 inverse is then just going to equal the identity. Okay, because G1 and G1 inverse are each other's inverse by the very definition. Okay, so this is equal to the identity, so that means that the entire thing is equal to the identity. So what I've just shown you is that if I compose G1 composed with G2 with G2 inverse G1 inverse this way round, I get the identity. Next, I need to show it the other way round, so let's now do it the other way round. So I'll take G2 inverse G1 inverse, and this time I'll compose it with G1 G2, but the other way round this time. Okay, so once again I'll color code this in. So here is G2 inverse G1 inverse, and here is G1 G2. Okay, now, again, what I can do is, let's work out the middle bit first. So we've got G1 inverse composed with G1 here. That will, of course, just equal the identity element, so this becomes G2 inverse G2. But because these two are each other's inverse, this is just, again, equal to the identity element. Okay, so again, I get that if I compose them this way round, I get the identity. So now I've done exactly what I need to do to prove that this is in fact G1 composed with G2's inverse. Okay, so what I can now do is use this little fact over here to fill in what G1 composed with G2's inverse is actually equal to. So now what I'm going to do is I'm going to modify this G1 G2 A, and now I'm going to turn G1 G2's inverse into G2 inverse composed with G1 inverse, and I want to show that this is going to be equal to little a for all little a is an element of the set capital A. Okay, so showing this is equivalent to showing this is now equivalent to showing that G1 composed with G2 composed with A composed with G2 inverse composed with G1 inverse is equal to A for all A is an element of the subset capital A. Okay, now, so we're going to try and show this, and if we show this, we'll have shown that G1 composed with G2 is an element of the centralizer of the subset capital A in the group capital G. Okay, so now is the point that we're actually going to use the fact that G1 and G2 are in the centralizer of A and G. Now what does that mean? Well, that means that if I conjugate any element of the subset capital A by either of these two elements, I will always get that element of the subset back again. Okay, and now I'm going to use that fact because look what I have here in the middle. I have G2A, G2 inverse, highlighted here in green, and I think I'll make it even more blatant by putting a great big box around it. Okay, so I have G2A, G2 inverse, which is the conjugate of this element little a in the set capital A under the element little g2 here. Okay, and what do I know? Well, because G2 is an element of the centralizer of the subset capital A in the group capital G, I know that when I conjugate little a, which is an element of the set capital A, by G2, I'll always end up with that element little a back again. Okay, so now I can replace G2A, G2 inverse with little a because G2 is an element of the centralizer of A in G. Okay, so now what this expression becomes equivalent to is G1A, G1 inverse. And I need to show that that's equal to little a for all little a is an element of capital A. But of course that's absolutely true again because G1 is an element of the centralizer of A in G, and G1 therefore will conjugate any element of the set capital A to give that element of the set back again. So G1A, G1 inverse will also equal little a for all little a is an element of capital A. So what I've now successfully done then is shown that if little g1 and little g2 are elements of the centralizer of A and G, that it automatically follows that little g1 composed with little g2 is an element of the centralizer of A and G, and therefore that the centralizer of A and G is closed under composition and does therefore obey the first axiom of group theory. Okay, so this is looking hopeful. So now let's do the third axiom of group theory. So I've argued already that we don't need to bother with the second axiom of group theory. So associativity is beautifully done for us already, which is a good thing. Okay, right. So axiom number 3 then of group theory. We need to have an identity element. Okay, and in the case of a subgroup, what that means is that we need to have the identity element from our larger group. So we need to show that the identity element from our larger group capital G is an element of the centralizer of A in G. Okay, so this shouldn't be too difficult. We just need to make sure that the identity element obeys the condition to be in the centralizer of A in G. Okay, so what was the condition to be in the centralizer of A and G? Well, it was that if we conjugate any element of the subset capital A by the element, which in this case is the identity, we must get the same element of the subset back again. So it needs to be the case, remember, that GA, G inverse, is equal to little a for all little a is an element of the subset capital A. Okay, so now let's just fill in for little g here the identity. Okay, so we'll put in the identity composed with little a, composed with the identity's inverse, but the identity is its own inverse, so this just is the identity composed with a composed with the identity. But of course, composing with the identity has absolutely no effect, even if you do it on both sides as we have here. The identity composed with a this way will just equal a, and then a composed with the identity, again, that will just equal a. So the entire answer here is just a, basically. So conjugating any element of the subset capital A by the identity truly has absolutely no effect, because indeed conjugating any element of the group by the identity has no effect. Okay, so the identity will absolutely always be in the centralizer of any subset capital A in the group capital G. So that's one element that you can always bang on being in the centralizer of a subset capital A in the group capital G. Okay, so we've just shown then that the identity is an element of the centralizer of A in G. Okay, so axiom number 3 then of group theory is satisfied for these centralizers. Okay, right. So the fourth and final axiom of group theory then now. Okay, so the fourth axiom of group theory then is that if we have a little g, which is an element of the centralizer of A in G. Okay, now I might just add in for all little g is an element of the centralizer of A and G. Okay, so you take any element of the centralizer of A and G we need to make sure that its inverse element, which we know will be in the group capital G, because the group capital G is a group, so it must have an inverse, okay? We need to make sure that that inverse element is also an element of the centralizer of A and G. So what we've got to show, basically, is that G inverse, which is certainly in the group capital G, okay, so if we've got little g here, we'll absolutely we'll have an inverse element to that somewhere in the group. We need to make sure that that inverse is also in the centralizer of A and G, so that this centralizer of A and G actually does obey the axioms of being a subgroup. Okay, so we need to show that G inverse is also an element of the centralizer of A in G. Okay, right. So how are we going to do this? Well, again, we just need to say that G inverse needs to actually obey the condition for being in the centralizer of A and G. So we need to prove that if we conjugate any element of the subset capital A by G inverse, so if we take G inverse A, G inverse's inverse, so conjugating this element little a by G inverse, we need to prove that that is equal to little a for all little a is an element of the subset capital A. Okay, so this is what we need to do in order to prove that little g inverse is an element of the centralizer of the subset capital A in the group capital G. Okay, so the first thing that I can do is reduce this absurd notation here. So G inverse's inverse is in fact just equal to the element little g. So the inverse of G inverse is equal to G. Okay, so G and G inverse are each other's inverses basically. So what we need to prove then is that G inverse A G is equal to little a for all little a is an element of the set capital A. Okay. And what are we given then to try and prove this? Well, we are given the fact that little g is an element of the centralizer of A and G. That's all we've got. That's the only reason we've got to believe that this could possibly be true. Okay, so what does it mean to say that little g is an element of the centralizer of A and G? Well, it means that if I conjugate any element of the subset capital A by little g, so if I take GA G inverse, that's always going to equal little a no matter what little a we're working with in capital A. So this is my great idea, okay, and this is a great trick. This is rather lovely. This is one of these nice tricks that just does the job easily, but which you might not think of, or at least it would take you a while to think up it. Okay, so watch this trick and appreciate how nifty it is. Okay, right, so what we're going to do is we're going to use this fact. Okay, we're going to use the fact that if you conjugate any element of the subset capital A by G, it gives you A back again, okay? And when we're considering what is little a conjugated by G inverse here, what we can do is stick in, for little a here, GA G inverse. Okay, so what we're going to do is read this equation backwards, basically. If it's the case that little g conjugates any element of the subset capital A to give little a back again, then surely what I can do here is when I'm trying to conjugate little a by G inverse, I can just insert in place of little a here, GA G inverse. That is perfectly true. Okay, whatever little a you're working with in the set capital A, it's perfectly true to replace little a here with GA G inverse, because GA G inverse, whatever little a is, has to be equal to little a. That's exactly what I've got over here. Okay, and now I'm going to actually use that fact. So I'm going to insert this in. I'm going to substitute it in here. Okay, so what I'm going to now say is that G inverse AG is actually equal to G inverse, and now I'm substituting in GA G inverse G. Okay, and now you see how clever that is. Okay, because what have I got in the front here? I've got G inverse composed with G, and of course we know we don't care about these brackets. We know in group composition we've got associativity, so it does not matter where you put the brackets. The answer is the same. There is one and only one answer to what this composition of 5 things in the group is equal to. It really does not matter where you put the brackets. Okay, so we can put the brackets around G inverse G here, and we can put the brackets around the G inverse G over here. Okay, and those two things are both equal to the identity, so this becomes just equal to little a. Okay, and that's true no matter what little a you're working with. You can do that whatever little a you have there, okay, because this held true for all little a is an element of the subset capital A. Okay, so because of that, we can prove that G inverse is also an element of the centralizer of A and G. So if you've got any element of the group within the centralizer of this subset capital A in the group capital G, then its inverse element in the group, G inverse, will also be in the centralizer of A in G. Okay, and that therefore proves that the centralizer of A and G is indeed a subgroup. Okay, so we'll have a break there, and in the next video what we'll do is talk a little bit more about centralizers, and then we'll move on to normalizers.